To describe an object released from rest at a height h with the goal to solve for the total time t of the resulting fall, students A, B, and C write three different formulas that are shown there in the slide, these three different formulas. And it asks us which one is correct. Well, let's look a little bit about like how might one have arrived at each of those formulas, and then we can decide which ones, if any, are correct. I don't think we're limited to choosing only one. It could be that more than one is correct. So let's look at student A. I think student A, they probably drew a picture of free fall here and recognized that it fell through some height h. And they might have thought about the first kinematic formula and looked at some of the variables in it. So this is pretty correct. What I'm looking at so far here, and what the student probably did, is to look at this formula as describing a process, and then thinking about, because this formula is really kind of generic. It can apply to any process, but we're thinking about something very specific here. So how do I change things to fit this specific situation? And if I say the thing fell through a height h, and let's say it started up here, and maybe my origin is where it landed, then one way of making that statement is to say, well, x naught is equal to h, right? It also says the object was released from rest. So a way of making that statement is to say, well, v naught is equal to 0. And it's falling down because it's on Earth. So one way of saying that very explicitly, I like to call this the explicit minus sign choice, is to say that A is equal to negative G. And then if you substitute these things into the first kinematic formula, you'll get pretty close to what I've said here, where I've claimed that student A is actually going to write. Maybe the one additional thing I want to say is, since we're talking about the process where it winds up falling on the ground, and if I associate that with a position of 0, then I should make the statement that x is equal to 0 and then make that replacement as well for x. So in other words, again, this is generic, but now specifically with these replacements, and therefore specific to this situation, I would get 0 is equal to h, since h is replacing x naught. V naught is 0. V naught times 0 times t is still just 0, so maybe I could write a plus 0 there, and then I'd write plus 1/2 times minus g for the replacement for acceleration, and t is still just t, so we're going to leave that one. That one just gets to stay. But if you simplify that, you wind up getting 0 is equal to h minus 1/2 gt squared, and that really kind of explains what they were thinking. Now, you may have noticed that the formula that B has is actually algebraically equivalent to the formula that A has. So surely if A is correct with this, B also arrived at a correct answer here. But they may have thought about it differently to arrive at that. So let's look at how student B might have thought about this. Well, one thing that is still available to us is we had the specific formula that I've associated with Galileo's law of free fall. D is equal to 1/2 g t squared. And if student B simply said, you know what, I recognize that this situation, the way it's described, is exactly what this formula describes. The only difference is I was told to describe the height from which the object was released with the variable h. So therefore, I'm just going to make the replacement h is equal to 1/2 gt squared. And since I know this works for an object that's at the distance it fell, for an object released from rest with an acceleration of free fall equal to g, this should therefore also work. And so they arrived at that. And that was actually kind of easier than what student A did, and is also correct. What did student C do? I mean, theirs looks a little different, so surely they made a mistake, but maybe not necessarily, because if I look at this process for student A, if I did everything the same as student A did, okay, except with one change. If I said, and maybe this is the mistake, right? If I said A is equal to G, clearly that must be a mistake because it's different than this did, right? Or maybe you could argue, well, clearly it's a mistake because the object is actually falling down. Or is it? Right? This student might have been working under the assumption, making an implicit minus sign choice, that g is equal to minus 9.81 meters per second squared, as opposed to here, where I would say, and really for both A and B this was the case, that g is equal to positive 9.81 meters per second squared. So both student A and B explicitly understood that things fall down and then define g to just be a positive magnitude number. But there turns out there are sources out there and there are people who like to define g as a negative number. I personally don't like to do that. I personally think a lot of from talking to other physics teachers, I found the community is kind of moving away from this, I feel like. But on the other hand, I have met a few people who still like to do it this way. So with this, if you do the appropriate substitutions, again, into the first kinematic formula, so in that sense, if student C is kind of thinking the same as student A with just they're thinking about this minus sign a little bit differently, this explains pretty well how they got to the result that they did, because here it is, 0 is equal to h plus 1/2 gt squared. And as long as they're consistent with this choice for g, but recognize g would have to be a negative number in order to explain how things are falling down and not falling up in a standard coordinate system. There may be, one thing that's worth saying is, like, do you have to use a standard coordinate system? You could have down be positive and up be negative and potentially look at this problem that way as well. I don't think the way I've presented student A, B, or C are really doing that, but you could explore that and see what formula you wind up getting to. In that sense, in physics, there are actually quite a few choices for how to correctly tell the story and therefore get maybe a correct answer from that story. So at the end of the day, all of these are potentially correct. The only difference between C and the first two, A and B, is that for C, you have to assume a negative value for G. And again, I actively discourage that. So for me, when you look at how I do problems, I will pretty much always assume that G is a positive 9.81 meters per second squared, or maybe some other number if I'm looking at something like Pluto or some other planet out there. So that's what I recommend to do. But again, if somebody asks me, is it wrong? Not necessarily, as long as they were thinking about it correctly. One thing this brings up is you might say, oh my God, this is overwhelming. I don't know which way to choose for me to do. And I don't necessarily have a simple answer for that, because we're going to be looking at a lot of stuff. But one of the things it does highlight is, in physics, a big pitfall is to try to memorize solutions to problems. And then you get to an exam and you look at problems, and if I throw even just the slightest difference into those problems and you've memorized all your solutions, you think you're ready for your exam, and that throws you, which it often does. I've had this happen a lot, so I'm speaking from experience here, and I'm trying to kind of like let everybody know, don't do this. Don't focus so much on memorizing. Focus on the process. So I've looked at these three different thought processes. They're all valid. You need to develop your own. You need to practice and hone your skills, develop your own methodology loosely based on the feedback and the learning that you're getting in this class. But you need to be engaged in that process and not just memorizing other people's solutions, whether they're mine or from a textbook or from some other internet video or anywhere else.